Hey all, I want to go through the kinematics lab that you submitted this week. I want to give you some kind of general feedback for all of you. I want to walk you through how I put together this lab report. What I want you to do is you should have a copy in front of you. I highly recommend you print it and you make detailed annotations on your copy so that next time you have to write a lab report, you take it out and you're going to take the annotated copy out and you're going to make sure you address all these things on your new lab because every lab is going to build on each other. There's going to be some stuff that I talk about here that you couldn't have possibly included because we hadn't yet talked about it, but that doesn't mean we can't learn afterwards. So that's the goal for this lesson. So first, I put the title here. There's my title. Here's my name. Always put your name on your lab report. Put down who you collaborated with. I put no collaboration because I didn't. But if you collaborated with anybody, all those names have to go on there. That doesn't mean you're sharing a lab report. It means you shared information that is included on your lab report. Then I reworded the task as a question. You'll notice my question starts with, what is the relationship between? So this is how I like to start almost all my questions. I find that most lab questions have two forms. Either it's what's the relationship between X and Y, or it's what is the value of something. So those are the two labs we do most often in this class, and wording it in one of those two ways helps me to write a really good CER, and it also helps me to design the lab. So if we're looking for a relationship, what that implies is that you must have a graph, okay, immediately. So then I wrote my methods and materials. So I want you to read this through. I highlighted the materials. You do not have to do that. I did it because I want you to notice that there are no lists, right? Everything, all my equipment, I forgot one, is embedded, right? Embedded in this, in here. The other thing that you want to make sure you talk about is that you did multiple trials. So including information about multiple trials is how you're going to address uncertainty. And every single experimental design question on the AP exam, they ask you, or one of the standards is, did you address experimental uncertainty? So you did this, and also when you repeat something for 5 additional points, that's also how you address uncertainty, by doing many points and doing each point several times. Okay, it becomes more reliable. I have a picture here. Now, one thing I don't have in the picture that would make this better is to label all these things. So, saying that, taking this, right, and putting it into a text box would be a really smart thing to do, to label that. Where'd it go? Oh, yeah. So then you can put it here, right? So you make sure you label everything. I'm not going to do that now because I don't want to take the time. You can figure out how to do that, but it would be good to label everything. And then I have a picture, a screenshot of my tracking. So I include whatever it is I use. So I tracked the ball. You might have done this differently. There were several ways you could get the data. Then I have a data table. And you'll notice I have a lot of measurements, and not a single one of you had all these measurements. So I think there's one person who came close. But notice I have these heights, the initial heights, and I have the average speed, and there were 3 trials. Shouldn't say average speed, this should be initial speed of the projectile. And so each one, there were 3 trials, and then I took the average of those 3 trials. So we did that for every height. And then these are the horizontal distances and their averages. So in here are a ton of observations. Any observation I made, all the data collection must be presented. Okay, if you did multiple trials, you have to show all the trials. If you did multiple data points, you have to present all the data points. Most of you did not do that. This was not necessarily a requirement. You could have just put height 1, 2, 3, 4, 5, 6. That's fine. I prefer precision, so I just used capstone to measure it. All I did was I took the distance tool and I measured from where the ball was down to the tabletop. So. This is a sample graph. Notice I only included one. as a sample for my data collection. You don't necessarily have to show all. I think this is the graph made from the tracking, and probably it would be a good idea to have a label. So this is the graph of the projectile's motion along the horizontal axis, right? Because I only graphed the x position. So that means that at 0 meters, this is when I started tracking at 17.317 seconds in the video. And here's where I stopped tracking at 17.751 seconds. And it went 1.38 meters on the horizontal. It's on the horizontal because I graphed x position. I also found the trend line because I could use this trend line to find the initial velocity. And we talked about that last time. We actually found it on the horizontal ramp, and you might have used that. But I know, and you now know, that on the horizontal axis of a projectile, velocity is constant, right? So if acceleration is 0 on the horizontal, then whatever the velocity is here is the x velocity at the beginning also. So you can just use this one graph to find your distances and your velocity. So when you make a graph, part of the interpretation of the graph is writing out all this information. You can't just leave it on the graph. You need to write out the equation of the trend line using M and B. B is where you would hit the where time equals 0, so that's why it's negative 51. It's way back at the beginning of the video, which doesn't make sense. It has no real meaning here. So you're going to need to think that through. And then I have the theory here where the position equals v initial t plus 1/2 at squared. So where this here, the vi, is going to be your 3.18, and the time is on the x. So now you know what the initial velocity is for that horizontal axis. The other thing you can find out is the change in the horizontal position from the beginning to the end by just subtracting those y coordinates, and you can find the elapsed time by subtracting the x coordinates. So all that information is part of your analysis, and you want to state it. If you don't need it, that's fine, but I ended up using most of this stuff. Okay, so before I do that, before I talk about sources of experimental error, notice then I made a graph of range, or horizontal distance, versus the initial horizontal velocity. So I have all that stuff here, and this is the part that I think none of you did. So, and I'm not yelling at you, I just want you to know that that's really important, because if you're going to just look here and you're going to say, oh, when the initial speed goes down, the range goes down. So that is true, but it's very, very elementary. It is not okay at this level. So you can, make that statement, but it's way too general. How do I know that's a direct relationship, or a direct square relationship, or a direct square root relationship? How do I know if it agrees with physics theory if I don't know what the equation is? So it's just insufficient. In order to be able to answer the question, you must make a graph. So you'll see I graphed it, and I have I ended up with my trend line, y equals 0.4476x, which is range equals 4476 v initial, right? Because that's what I graphed on these lines. And therefore, this must be the hang time, right? Because here's the theory. So you want to, notice the same three things that I used here, but this I used to gather my data. This was data collection. This is analysis. So it's similar steps, but it's used for a different purpose. So this is the trend line equation. Here's my mathematical model where I substitute in range for y and horizontal velocity for x. So that's what I did here. And then using that, I can now see that delta D, VI, and therefore this must be T. This is the hang time because acceleration should be 0. So my experimental time is 0.4476. So another thing you should do in your sample calculations is to show them. In your analysis is to show some sample calculations. So what I did was I calculated using my problem solving method. I calculated the amount of time it would take to fall using the vertical distance. So I went back into my capstone here and I measured this distance here. Okay, so measuring this distance, I actually should have labeled, or I can actually add it here. So parallel to track, floor, which is 1.009 meters below. See, so you can actually include constants and things like that in your methods and materials if you forget to like label it or take a picture or something. So, that's fine. So I'm trying to show you some ways to fix and make your lab reports better when you know, especially as you notice things. So I got a theoretical value for hang time of 0.454. Well, using that, now I can find percent error. Percent error is theoretical minus experimental over the theoretical, and then find times 100. And doing that is about 2%. I rounded, which is fine. So those are all the different types of analysis I can do for this lab. Lots, right? This is pretty sophisticated, and you may not have known all of that, and that's fine, but I want you to learn from it and start trying to put it into your next ones. Last part, let's talk about the CER. So I highlighted it because the yellow is your claim, and the claim becomes really easy to write if you're answering the question, what is the relationship? Well, the relationship between the initial velocity of the horizontally launched projectile and the distance it travels before it strikes the ground is linear. Done. Okay. You can also say it's direct. That's fine also. Those are synonyms, but you don't need both. Okay, one or the other. My evidence is my mathematical model. So the mathematical model is range equals 0.44, I have a mistake here, 76 VI with a correlation coefficient of 0.9947. This means that 99.5% of the data fit the trend line that I chose. Why is this good evidence? Well, I'm showing that the range is directly proportional to initial velocity. Right? A linear equation means that there's a linear relationship. So if I present that equation, I've proven that it's a linear relationship. The correlation coefficient is there because it proves that the linear fit was an accurate one to choose, because I could choose any fit and Excel will do it, but if it's not a good fit, it'll give you a poor R-squared value. Does that make sense, right? Okay. Then the last part is the reasoning. So there's two parts. There's the physics theory, and then there's tying it to your results. So in theory, projectiles travel along the x-axis with constant speed because there is no acceleration on the x-axis. Therefore, using the kinematics theory, delta D equals VIT plus 1/2 AT squared, we see that our mathematical model mirrors this relationship closely. You could stop there. Bonus, the 2% error in our hang time strongly suggests that our lab reflects theory very well. It's a bonus, right? So that's a complete CER. And this whole part is all of your analysis, and then this whole part is your experimental design. Please reach out to me if you could use any help, or I also am posting under the modules a whole section of support for you with videos and documents to help you write up your lab report in the future.